Hello everyone, I'm Pragya Srivastava, VC Department, AKGEC Ghaziabad. I'm here to record a lecture in Control Systems, KEC 602, and Unit 4. We are discussing the stability of linear control system. In my previous lecture, we have studied and started what is Routh-Hurwitz's criteria and Routh-Hurwitz stability criteria to predict the stability of a system. So we will go ahead on the same topic. And we will study that how a polynomial, and that polynomial is necessarily the characteristic equation, how that characteristic equation framed in terms of a polynomial can tell us about the stability of a system. So let's solve the question using Routh-Hurwitz table. So previously also we were going ahead with the help of an example. Here also we'll try with the same approach. We'll take certain example. Let's say we are taking 4s to the power 4 plus 5s cube plus 3s square plus 2s raised to the power 1 plus 4 is equals to 0. So now we have studied that we have to construct a polynomial, a table starting from s raised to the power 4, s raised to the power 3, s raised to the power 2, s raised to the power 1, s raised to the power 0. And then we have to make this table out of it. Now, the first two rows will be framed from the characteristic equation itself, and we will just keep on writing the coefficients. So, the first row will have all the even coefficients, and the second row even because the 4 was even. If this, instead of 4 we have s raised to the power 7, then all the odd coefficients would come. Now here, since s raised to the power 4 is an even number, so all the even coefficients will come. So even coefficients are 4, 3, and then again 4. Next is odd coefficients, 5 and 2. So 5 and 2. Then here we don't have any. Now we have to complete the given table, and there are certain rules to complete this table. What are the rules? We have done this portion. This portion is done. We have to find out this. Now how can we find B1? So B1 is this into this. Yes. This into this. So what we are actually doing? We have to first of all multiply an minus 1 into bn minus 2. So here we have this term, 5 into 3, 5 into 3 minus an into an minus 3. Then we have 4 into 2 divided by an minus 1, which is this term. Like in this case we have 5. So this will be nothing but 5 into 3 is 15 minus 4 to 8 by 5. So this is how we have this term here. Okay. Another term, let's calculate, and let me erase the remaining portions. Then here I can write here 7 by 5. So here is this 7 by 5. Okay. Now another term. We have to write it simply 2 into 4, 3 into 0 upon 2. So of course that has to be 4. And then correspondingly the same process we will be repeating for another. The same process we have to repeat for another row. How we are going to do it? This into this minus this into this divided by 7 by 5. So here we can see that in this way, similarly, we will be making the complete table. Now, once we have made the complete table, we have to visualize it. So this is the rule position. Now we are going to take an example and solve a question on this. Of course, one more thing we have to see, that after we have made the complete table, we have realized the complete table, we have to see this row. We have to see this row, or we have to see, and examine this row. Okay, we have to see the changes in this row. Depending upon these changes, we can predict the stability. The number of roots in the right hand side of the S-plane is equal to the number of sign changes in the first column of the Routh array. This is called a Routh array. This particular column is called the Routh array. So let's say this column is, I'm taking an example, I'm writing a column 5, 10, 2, 6, 8. So this is case 1. How many times the sign is changing? There is no sign change, so it is 0. The answer to this question is 0. So the sign is changing 0 number of times. So we have 0 roots on the RHS. So system becomes stable. Let's take another example. Let's say it is 5, 10, minus 2, 6, 8. So how many times the sign is changing? Here to here, no change. Here to here, it is changing. So it is 1. 1 for the first time, it has changed. Here to here, it is again changing from negative to positive. So it is 2. So 2 times the sign of the coefficients are changing. So we have 2 poles on the right hand side of the S-plane. So it means the system becomes unstable because you have 2 poles. Even if you have one single pole, the system becomes unstable. Let's say another example is 5, 10, 2, 6, minus 8. So here to here, no change, no change, no change. Let's say this is minus 8. And then again, you have a change here. So how many times the sign is changing? 1. So you have 1 pole on the right hand side and the same system becomes unstable. So even if you have one single sign change, it means you have single root on the right hand side and the system becomes unstable. So this is how you have to visualize and see the stability. Next, we have a given example. Here, GS is equal to 1 upon S cube plus S square plus 2S by 23. And then we have negative, it connected the same system to a unity gain negative feedback system. And then we have to find the overall transfer function. The closed loop control system, which is having the transfer function Ys by Rs, is 1 upon S cube plus S square plus 2S plus 24. Of course, you have calculated and made the changes. So you have substituted the formula GS upon 1 plus DSHS, and then you have find out this is the transfer function. What is the characteristic equation? Characteristic equation here will be equal to 0, this portion. So this becomes the characteristic equation. So it is very much eligible for Routh-Hurwitz criteria. Why? Because it has none of the coefficients are exponential or sinusoidal or trigonometric, and all the terms are available, s raised to the power 3, 2, 1, 0. So no term is missing. So we are good to solve. So let's start. S raised to the power 3, s raised to the power 3, s raised to the power 2, s raised to the power 1, then s raised to the power 0. So since 3 is odd, we will write the coefficient of all the odd. Odd is 1 and 2. Even will be 1 and 24. So this term will be 2 minus 24 divided by 1. So it has to be minus 22. Minus 22. See, minus 22. Next has to be 1 into 0. 1 into 0 divided by 1. So again it has to be 0 here. That is 0. Next is 22 minus 22 into 24, this term, minus 1 into 0, that is 0, divided by minus 22. So this becomes 24. And of course this will be this into this, 0. So here we see that we can compare the two tables. 1 to 124. 1 to 124. Already available. Minus 22, 0, 24, 0. Minus 22, 0, 24, 0. Now we have to see this column. So since from here to here there is one sign change, and from here to here there is another sign change. So first sign change is there from 1 to minus 22. The second sign change is there from minus 20 to 24. So there are two sign change. So two sign change means two roots lying on right hand side of S plane. So hereby the system becomes unstable. Routh array for closed loop control system with TS is equals to this one, and here we can very easily see that the closed loop transfer function defined by this block diagram is an unstable system. Now we have to see certain special cases. What are these special cases? Routh stability criteria special cases. In these special cases we will see that what happens when the first element itself comes out to be 0. So the Routh table has 0 only in the first column of the row. Another case is Routh table has the entire row which consists of zeros. Let's calculate this row. This is 3 into 3, 9. 9 minus 4. So here, and that has to be divided by 3. And here 3 into 0. It should have been 3 into 3, and it should have been like something 3 into 4 minus 4 into 3. So it is 0 only. Let's say 4 3 are 12 minus 12 again. So then it will come out to be 0. So this example can be reframed like this. And then further we have 3 into 0 minus 3 into 0. Of course that is 0 only. So what will happen if the complete row turns out to be 0? What happens if the first element itself turns out to be 0? So the substitution to these special cases is we have to let that this is not 0, but this is some alphabet zeta, some alphabet x, some alphabet L, according to your choice. So then we have substituted zeta here. So the next row would come like 4 zeta minus 2 into 6 is 12 divided by zeta. And then next term is 10 zeta minus 0 by zeta is 10 only. This will come like, let's say this be x. So 6x, let me write 6 into x minus 10 zeta upon, of course this is x. Okay, here we have another term. So in this way we can see that yes, So in this way we can see that this zeta can be predicted from the value, and we can see that we have to visualize that if 0 appears in the first column of a non-zero row, the route array replaces it with a small positive number. In this case, Q has some roots in right hand side. What is happening? Here zeta is coming out to be unpredictable. So let's say we can substitute and we can visualize this row now. What we are doing? Zeta is nothing but 0, we know. Substitute 0 here. So this is 4 into 0. 4 into 0 minus 12 upon 0. Upon 0 is infinite, fine. But that infinite comes with a negative sign. Like minus 12 by 0, it will be minus infinite. So it means from here to here we are changing the sign. Q roots has some roots on the right hand side. So we can see that the two sign change, two roots on right hand side of the S plane. So we can predict that the system is unstable. We don't have to stop when the first column comes out, when the first element of the first column comes out to be 0. We don't have to stop. We have to put it with the help of zeta. Same is the example here. Here also we can see that 7 into 6 is 42. Minus again 42 coming out to be 0. 7 into 8 is 56. Minus 56 coming out to be 0. So what will happen here? What we are going to do now? So what we are going to do, we will use this equation. Okay. So this S will be given the power just next to this, and we will write it 7s to the power 4 plus. We call it auxiliary equation. We are making an auxiliary equation. 42 into s raised to the power, this 7 was with s raised to the power 4. 42 will come with the even polynomial, even power, and the next smaller power. So it will be 42 s raised to the power 2 plus 56 s raised to the power 0, and that is nothing but this polynomial as coming to be like this. Now we have to differentiate it now. Differentiating it, we will get 7 into 4, 28s cube plus 42 into 2, 84s plus 56 will be given as 0. So these terms will come here. You can write as 28, 84, 56. One more thing you can do. Before doing this, you can reduce this equation here itself. You can reduce it, divide the complete equation with 7, and you will reduce it here. And then you can differentiate and find out, like 1s to the power 4, 6s to the power 2 plus 8. So we can see that we have to take this polynomial, take the derivative, and derivative can be written here, but as I have said, they are trying to reduce it. So they are reducing it. So after they have reduced it, see this, after reducing this, we will find out this polynomial as 1, 6 and 8, and 4, 12 and 0. 4, 12 and 0. We have to differentiate and then take the derivative, and in this derivative we have to we can, you know, we can write it as 1 s to the power 4 plus 6 s to the power 3 plus 8 s is equals to this will be square, and this is s raised to the power 0. So 0 means s, that is anything raised to the power 0 is 1. So this has to be a constant term. So this is 4s cube plus 12s plus this is a constant term. Here also it should have been 0. And then we have this 0 equal to, then the coefficients which we have is 4, 12 and 0. We are writing 4, 12 and 0. Okay, 4, 12 and 0. So we are again dividing it and getting 1 and 3. Now we can solve the equation very easily. Now there is no sign change, so there are no poles on the right hand side and the system is stable. So this is how we can solve a Raoult-Hurwitz table and predict the stability. In my next lecture, we will study about root locus. Thank you.